Before machine learning, there was statistics. In this prologue lecture notebook for Module 6, we will briefly review linear regression to help set the stage and mindset for learning models from data. Linear regression is a commonly studied topic in statistics and computational science. The concept of linear regression is also at the core of many machine learning algorithms, which makes it a great place to start our studies. Now, why are we motivated to study specifically linear regression besides the reasons I just gave? It is a widely used technique. It runs fast. It is easy to use. There's not a lot of tuning of hyperparameters required, which is often necessary in more advanced machine learning algorithms. It is highly interpretable, meaning we can understand what the outputs are giving us and why they're giving us those results. And it is the basis for many other methods. For example, we will see how artificial neurons are related to linear regression in the Part A lecture notebook that follows this one. The libraries that we're going to use, besides pandas and matplotlib, the pyplot module with matplotlib, is going to be scikit-learn. We're going to use that to perform the linear regression. We will learn a bit more about scikit-learn in this module if you continue on with the lecture notebooks in here, but you could devote an entire course to this library and still only scratch the surface of what it has to offer. It is a very good module for you to focus most of your energy and attention on as you learn machine learning and data science, since it provides a lot of the functionality for machine learning that you would in general need to use. We do a very targeted dive into classifiers available within scikit-learn in a Part B lecture notebook. At least that's planned. That material still has to be made, so it might not be there for a little while. It depends on when I have time to create that, because that's supplemental to what we'll have time to complete in the course. So it'd be something that eventually will go up on the GitHub repo. So that's kind of a big overview. I'm going to go ahead and run this code cell and let everything connect and load the pandas library. And I'll just briefly discuss the learning objectives. We want to be able to apply linear regression models to data. We want to be able to interpret linear regression model coefficients. We want to be able to apply linear regression to polynomial models of data. And we want to be able to apply multiple linear regression when there's multiple features. We also want to apply dummy variables to categorical variables in order to perform linear regression and interpret results. So we're going to see quite a bit. We're going to learn quite a bit how to do, but hopefully, because it's a very data-driven problem, there's a lot of conceptual understanding, I think, and interpretation that's fairly straightforward, that it's not too onerous of a task. And with that, we will just about begin. We begin by using pandas to read in a data set that I have on the repo. The data set is kind of a fake data set where it describes the sales of a company's widget, something that they've made that's associated with different advertising expenditures in terms of TV, radio, and newspaper expenditures. So you can go look at the data set within the repo. You can just copy and paste this URL to look at it. I'm going to go ahead and read it in. I'm just going to show you what the shape of that data is. It has 200 rows and 4 columns. If you actually want to look at the data frame from the CSV file, you see there's the TV, radio, and newspaper expenditures on those types of advertisements for different markets. There's 200 different markets, and then the sales associated with that. So you can imagine these are in different units, like maybe these are in thousands of dollars, and maybe these are in millions of dollars or hundreds of thousands of dollars. So the numbers aren't really so important. It's just more for illustrative purposes. But the first 3 columns are all about the expenditures, and then the sales is really kind of about revenue that is generated based in these various markets. And so you would try to make some sort of judgment or assessment or analysis. How much does advertising impact sales? So if you just look at for instance, like the first 5 rows, we see that we are spending quite a bit at different amounts on TV and radio and newspapers, not as wildly varying, at least from what we see there compared to the others. And then we see the sales are quite a bit different in these different markets. So what would we call the features of this data? The TV, radio, and newspaper, those advertising dollars that are spent are the features. And the response variable we're interested in is the sales. All right, so the inputs that we're kind of interested in figuring out, like do these values change a response? Those are the things we call a feature. And then the things we're looking at how they change as a function of these features is what we call the response. And that would be the sales. Okay, and it looks like I have these here where I describe the units as in thousands of dollars for these different expenditures, and then this in thousands of widgets is what the sales are. So there's 200 observations, 200 markets in the data set. If you want to visualize the relationship between the features and the response, we can use scatter plots. The nice thing with pandas, and we haven't explored this too much, is that a data frame has a plot command associated with it. So I'm just going to go ahead and do that now. I'm going to create a figure and axes, and then I'm going to populate with the matplotlib/pyplot module that I've imported as PLT right here. And then I'm going to use the plot method associated with a data frame object in order to create scatter plots of the various sales versus the different features, the TV, radio, and newspaper. And I'll specify, because it's an array of 3 plots, which of the axes, 0, 1, or 2, should I be putting the scatter plots in. So if I just do that here, and what's nice is with this plotting, you don't have to add labels. It's kind of all there. Like, these are the labels that are associated with the different plots, and it's just grabbing the features based on the column names associated with the data frame. And we just see here are the plots here. And it looks, pretty straightforward immediately that I would say if you looked at the sales versus TV expenditures, there seems to be the strongest functional relationship there. Everything else is a little bit more noisy. So this would be a good place to start in terms of trying to understand a relationship between sales and TV expenditures, TV advertising dollars spent. So this leads us to our just general questions about the advertising of data. Always a good idea to visualize the data and then try to come up with the questions we'd want to ask. So let's pretend you work for the company that manufactures and markets this widget. The company might ask you the following: on the basis of this data, how should we spend our advertising money in the future to maximize profit? This general question might lead you to ask some more specific questions. Is there a relationship between ads and sales generally? How strong is that relationship? Which ad types contribute the most to sales? TV, newspaper, radio. What is the effect of each ad type of sales, and given ad spending in a particular market, can the sales be predicted? So these are all questions that we will explore the answers to below, and we'll use simple linear regression. Simple linear regression is simply an approach for predicting a quantitative response using a single feature or predictor or input variable. So we will also look at multiple linear regression later on, where we consider all the different types of ways in which we can spend advertising dollars. But for now, we're just going to pick a particular feature, which is the TV. So in that case, you have this one feature and you have this one response. And simple linear regression generally starts with a line, although you can have linear regression. This is a linear response. You could have a linear response with a polynomial formula for the feature variable, because it's linear with respect to the coefficients. So we'll discuss this a little bit more. If that didn't make sense, don't worry, we'll get to it. Just the point is, if we start with just first a linear approximation, we say, okay, y is the response. So in this case, it would be like the sales. X is a feature. In this case, we might start with TV. Beta naught is the intercept. So beta naught would describe conceptually what is kind of the value of y, the response, like the sales that you would anticipate if you didn't spend anything on advertising, right? Just the fact that this widget, this product is out in the marketplace, it just is on shelves somewhere and people see it. Some people are going to buy it with no advertising. They'll just look at the packaging and they'll make a decision whether to buy it or not. So there will be some sales even if you don't market it at all. But then you have this idea generally that if you advertise, it should drive sales more. And if you think that there's a straightforward linear response, you would say, okay, well, I think there's the sales I would get from no advertising, and then the incremental increase of sales I would get for each additional dollar or thousands of dollars of advertising revenue I spend on, let's say, TV advertising. And so this beta 1 is interpreted as the coefficient, kind of the incremental. As I increase the spending on X, like how much is this increasing what Y is? So these are called, beta naught and beta 1, the model coefficients. To create your model, you must learn the values of these coefficients from the data. And then once these coefficients are learned, we can then also use the model to predict sales. In this case, because sales is the response variable. So how do we estimate or learn model coefficients from data? Well, generally speaking, coefficients are estimated using the least squares criterion, which means that we find the line mathematically which minimizes the sum of squared residuals. This is the traditional line of best fit you are probably familiar with from other courses. So it's also something sometimes referred to as minimizing the sum of squared errors. So kind of conceptually, the idea is you have a line that you're trying to fit. This is your beta naught plus beta 1x line. You have your actual y data that's not on the line. There's some kind of noise. The line is just the kind of the best prediction that you would make for a given x value, what the y should be. And you look at the distance from each point to the line. You just draw a vertical line from the dot to the slanted line, and then that's the residual. That's how much error you make using the model to make the prediction. If you position the line at different points, then the size of this vertical line would change for each of the different points. So you take your model prediction, let's use hats at each of the, let's say, xi values, and then so this would be, these yi values would be given by beta naught plus beta 1 times xi, where xi is a particular data point. So if in our data set n is 200, and we would loop through like all of the TV advertising revenue, and for a given beta naught and beta 1, we could compute 200 predicted sales values for y, and we would call those the yi hat values. We would subtract the associated true values, the observed values that we have. We would square those differences. That's the square of the residuals or the square of the errors. We'd add all of them up, and then this creates essentially like a big parabola. You can think of it that way, where we're trying to, over the beta naught, beta 1 space, and you're just trying to find the minimum, like what values of beta naught and beta 1 minimize this response of the sum squared residuals. That's what's going on conceptually. Again, if you don't have the math background for that, it's not a big deal. We want to minimize this. We want to figure out what beta naught and beta 1 values minimize this. So, there's more things that I've written here, or that I've really borrowed from where this content was originally designed for, and I have linked above. But I'll just kind of start going into this. We're going to use scikit-learn to do the heavy lifting for us. So we're going to estimate the model coefficients for sales as a function of TV advertising data using linear regression. And we're going to use the linear regression model in scikit-learn. So what we do to do this, we're going to create a set of x and y values just so that we match notation with our variable names with what was shown above in these pictures. So I'm going to describe the feature columns I'm interested in. In this case, it's just the TV, right? So that's it. I just create a list with the TV here as a string because that's the name of the column in my data frame. And so then that defines my x data, and my y data is defined by the sales. So I just run that. That's simple. So now I just have x and y data, just so it looks like the labels of the axes that you see in these pictures above. So now from the linear model subpackage or the sub module of the scikit-learn, I'm going to import the linear regression object, okay, or class. And I'm going to then do the following three things, which is a usual pattern for scikit-learn, but it's also a usual pattern for any kind of machine learning algorithm that you would do. You would import the class of kind of algorithms that you're interested in using. So it usually gets imported from a library. You then instantiate, so you create a particular object based on that class, and then you call a fit command usually to learn the coefficients, all the kind of parameters, like hyperparameters you need, in this case the beta naught, the beta 1, associated with the model you're trying to learn. That's a usual pattern that you would follow in any kind of machine learning library. So here's my instantiation. So that is step 2. So the step 1 was importing linear regression. You don't only do that necessarily once. Now I have this class. I can go ahead and instantiate the object, LM for my linear model, LM for linear model. You can call it whatever you want. I'm just using LM. And then I fit. I pass it the data, the x and y data, and this is what learns the beta naught and beta 1 values from it. That's it. That's how I can perform linear regression. I don't have to do any other coding for me. There's just this kind of output you don't have to worry about generated by that code. And now I can print what the intercept and coefficient are. These have these underscores attached to them. You can just see what they are by the dot convention and looking at autocomplete. You can look deeper into the code. There's lots of ways where you can kind of explore what is associated with these linear model objects. So I'm just going to print them, and you see, okay, here's the intercept. So we just sell, it looks like around 7,000, a little over 7,000 of these widgets if there's no advertising. And then effectively for each, I think, $1,000 that we spend on on TV, because it's in units of thousands, we generate 0.047 more, I think, thousands of widgets sold. So that's the interpretation of the intercept and the coefficients. So that's exactly, I think, what I've described here. And in terms of interpreting model coefficients, you should read this, more closely because I give some additional language there. But let's talk about using this model for prediction now. Let's say that there was a new market where the TV advertising spend was going to be $50,000. What would we predict for the sales in that market? Well, we would take our beta naught plus beta 1x, and our beta naught approximately, I just kind of coded this up, or just written this in there. There's that 7.0325, and then there's the 0.047537, and times 50, because it's in units of thousands of dollars is the x. And whatever the output of that is, I can just manually calculate that, of course. That's what this code cell shows. And I say, okay, it looks like about 9.41 approximately thousand widgets would be sold. I could also manually calculate the prediction in a slightly better way by just calling these values, these intercept and coefficient values. That way I'm not rounding, which is what's being done here. I'm just kind of just looking at these values and rounding, just using some of the digits. So I could use more of the digits and get that output, and it's effectively the same. There's just a little bit of rounding that occurs in some of the later digits. And we see we would predict sales of about 9,409 widgets, like I said, 9,410 about widgets in that market. Of course, what we really could and should do is use the linear model object to make the prediction. So in general, to do that, I'm going to show you a couple things here. It is expecting this object that there are multiple features in the model, and that's something we're going to see later when we do the multiple linear regression. So what we need to do is formulate the input as either a 2D array or as a data frame. So I'm going to import NumPy as MP right now, and I'm just going to create like this array of predictions where if I wanted to predict it and it was a single market, I still need to do a 2D array, so I have those double brackets. So this is kind of a bit of something of a review of the dimensions of NumPy arrays, but we've seen this from module 2. So if I run that, then that linear model object has a method called predict attached to it. So lm.predict calls the method, and then I pass it an array, a 2D array, and then it will return the outputs. And in this case, so it creates this user warning, but you can kind of ignore it if you just want to look at it. It says like the X data that I'm giving does not have valid feature names. It's because it kind of wants to have a data frame more generally than just a NumPy array. So anyways, the output you see is effectively the same. It's just using the predict object from the module instead of you having to code up something like this, either kind of transcribing the values or copying and pasting them, or calling the data attributes from the object. You can just call this predict method, and you're generally going to want to do that because these models can get a little bit more complicated. But the better way, what you should really be doing, I just showed you, this is one way and it works, and of course there's a warning attached to it, is you should create a data frame, and you should use a dictionary for that, and you can just then list, here's the features and here's the different values associated with those features. And now this is my predict data frame. So I'm just looking, this is how you can create a data frame just with this type of dictionary. So it just has one row. I could of course say there's 50, 100, maybe 150, maybe there's all these different values I'm considering doing. So this creates this other type of data frame there. But I'll just go back to one. So it's just, there's one new market, but maybe you're evaluating potentially several new markets. And so now I can just pass the data frame directly to it, to that predict function, and no warning. So this is the nicer way to do it. This is really how you should do it, but I do want to show you that, if you just want to quickly do something with an array, it's maybe slightly less work than creating the data frame. So you could do it with that, but I would recommend using the data frame. So I'll just pause the video right there. That's something maybe you should play around with a little bit. Make sure you can do those steps, and then we'll come back and look at plotting. So what I'm showing in this very short section of the notebook is how to plot the least squares line, where you go from the smallest to the largest observed values of a feature, and then use the predicted values associated with that min-max to plot the least squares line. So what I'm going to do, just kind of zoom in a little bit here, is I'm going to create a new data frame, and I'm going to take the TV data. I'm going to use the min method associated with that series, because that's actually numerical series of data there. And then I'm also going to take the max value of that data, and then that's going to create this new data frame with the one feature of TV. So if I just run that, you see there's the TV expenditures, there's the min value and the max value. I can now look at my linear predictions associated with that new data set by using the predict method associated with my linear model. And I can see here's my array of values of min and max predicted sales data associated with the min and max TV expenditures for advertising. And so then I can create my scatter plot as before. I'm not creating the figure this time. This will automatically create the figure. The reason I created the figure previously was I wanted to create a figure with 3 axes in it. I'm not doing that here. So this will immediately create the figure. And then I also want to plot on that same axes, that's in the one set of axes that's in the figure, the new values. There's two values. This has the min and the max. This has the associated predictions. I'm going to plot that in red with a line width of 2. So if I just go ahead and run that code cell, there you go. There's my prediction, that least squares line, the line of best fit, the regression line. All these kind of terms mean the same thing. And there's my scatter of data. So that's it. That's a quick way to generate your linear regression visualization, your line of best fit. What we haven't talked about yet is really how well does the model fit the data, right? You can always find a line of best fit. It doesn't mean the line does a good job of explaining the data at all. It's just the line of best fit. And the line of best fit may be complete garbage. It's a line of best fit, but maybe the data actually follows like a more complicated trend. So the most common way to evaluate the overall fit of a linear model is by the R squared value. R squared is a proportion of variance explained, meaning the proportion of variance in the observed data that is explained by the model, or the reduction in error over the null model. And the null model is one that just predicts the mean of the observed response. So there's kind of think of that as no intercept and no slope. The R squared value is something between 0 and 1. Higher is better because it means that more variance is explained by the model. So here's an example of what it looks like. This in this figure here. Again, I didn't generate this. The original people that made the original version of this notebook I'm basing it on had this figure. So you can just see like there's these higher R squared values as you're using more complicated models. This is just higher order polynomials, n equals 1, 2, and 3. So you can see that the blue line explains some of the variance in the data, like R squared is about 0.54. That's actually in general like pretty good and for a lot of real data sets. The green line explains more of the variance. R squared is 0.64. The red line fits the training data even further, so R squared is 0.66. Although I would say that that red curve is maybe looking like overfitting, because if you look at what's going on with that red curve, and I know it's a little bit of a fuzzy picture, but it's swooping down. Like there seems to be definitely like kind of a negative trend in the data overall, and maybe it's leveling out a little bit here. But if you look at the red curve, it starts to have this trend where it looks like it kind of comes up a little bit, and then it starts to go down instead of maybe leveling off. Even the green, like it's not clear that just because the R squared value is getting better, that you do have a better model. In general, in fact, as you make your models more complex, especially if you increase polynomial order, you will typically see there can be things with precision in the arithmetic world we live in on a computer. But theoretically what happens is as you make more and more complex models, your R squared value will get higher, which means you're doing a better job of explaining the data. But it doesn't mean that you're developing a better model, because you might be overfitting to the data. And an example of that is really seen, let's say, if I look at this figure up here, this original one, right? The data that you see over here on this figure, it looks like there's a linear trend. Like generally, even though the values kind of go up and down, generally the trend seems to be as you increase X, Y increases. And a linear model is the simplest model that seems to explain this trend. And we don't really seem to have a lot of evidence to suggest it should be a more complicated model. However, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. And so what that means is if we used, I believe, certainly if you use the ninth order polynomial or 8th order polynomial, you could fit all of these data points. Like you could pass through all of it, and then your sum squared error is 0. But your model would be oscillating like crazy. And you'd kind of have to ask, like, well, just because I can use that model to get all the data I have, is it useful for predicting data I haven't seen yet? Like if you were to look at an X value that was, let's say, right over here, like right where my cursor is, I don't see if you see, but I'll bring it up to this line. You see there's this value above and below the line. And if you were to try to predict what Y would be for an X value that was between the X values of these two, you probably would think the line value looks like a pretty good estimate. But if you were to fit a really complicated curve through here, you might have a curve that's swooping down between these two. And you go, wow, like that might be way off from what the actual value is, because I'm really just fitting exactly to this data, but I'm not really fitting the trend. I'm like fitting the noise. like all these little unexplained variations that my models shouldn't maybe try to explain. I just want to capture a trend in the data and not necessarily capture all these other little variations that are too complex to be captured in my otherwise statistical representation of the trend. So that's something to keep in mind, is just because you have a higher R-squared value, just because you're explaining more variation in the data doesn't mean you actually have a better model. You might have a model that's fit too much to the data and it's just like oscillating like mad. You can imagine here with this data, you have a curve that's just jumping around all over the place and it could pass through and interpolate all of these values, but it would look like complete nonsense. It's not a very simple model. And in general, you want to use the simplest model you can to explain as much of the variation as possible. And there's a trade-off. The more complicated you make the model, the more variation you can explain, but the less interpretable, maybe the less realistic, the less generalizable that model can be. So that's really something you need to keep in mind. You want a balance of simplicity, and you do want to explain something in the model. You do want to have some explanation of variance and some good capture of the trend. And the trend might be complicated enough that it does necessitate a complex enough model. But again, these are things you have to use some judgment about and do some comparison. And one thing you can see here is, like, if you go from an R-squared of 0.64 to 0.66, that's not much of a change. You know, for basically going from a second to a third order, that barely changed anything at all. And you might kind of go, boy, as soon as I see that, maybe I'll just use the second order because it's simpler than the third order. It does a pretty significantly better job than the line, right? This doesn't really look like a line. It looks like maybe there is this curvature to the data, but I would say it kind of looks like part of a parabola. I don't know that I have enough like qualitative or quantitative information to really justify using a cubic model for this. So again, there's some judgment that you have to use here in terms of how complex your model should be. But if you want to see what is the R-squared value for the model, we did a linear model. We did a first order linear model line. So for our data, we can just look at it and we see it's like 0.611, and that's good. I mean, is that a good value? It's kind of hard to say. The threshold for a good R-squared value generally varies wildly on the domain that you're looking at, whatever domain of science or data that you're looking at. So it's most useful as a tool for comparing different models, but again, it will generally go up, it will increase as you increase the complexity of your model, but that doesn't mean that you should increase the complexity of your model. You have to have some judgment in there. So with that, we're going to pause the video. You might want to go read a little bit more about R-squared values and then also look at this activity 1. I'll go over the instructions and the solutions in this part of the video. So in this first activity, we will talk about linear polynomial regression as opposed to just linear regression. When you say linear regression, you generally just mean with respect to fitting kind of like a line of best fit, but you can also have linear regression to a polynomial model. And so the trick to adapt linear regression to nonlinear relationships between variables is to transform the feature data. The basic idea is to create a linear model that looks like this. So I say like y equals beta naught, I won't highlight that, we'll zoom in, y equals beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 and so on. And here, the x1, x2, and x3 and so on just involve functions applied to the single dimensional input x. So that is, we let x sub n equal some function like the nth function of x. It's just some transformation that transforms the feature space. Okay, what does that mean here? Like, let's take an example. If we're working with polynomials, then f sub n of x is equal to x to the n power for some n. Then a polynomial regression problem will look something like this. Y equals beta naught plus beta 1 times x plus beta 2 times x squared plus beta 3 times x cubed and so on up to whatever order you think is there. So if you come back to this example we were just looking at with this figure, if you were to say, oh right, there's one feature here, this x-axis here, this whatever this data is, and I could think of that, there's that data squared, that data to the third power if I go to the n equals 3. And then I'm just looking at trying to estimate the coefficients, the intercept, and then beta 1, beta 2, and beta 3, which are the coefficients associated with that feature raised to the first power, feature raised to the second, and feature raised to the third power. So the model is still a linear model, even though there's this polynomial involved. The linearity is referring to the fact that the coefficients never multiply or divide each other. So it's a linear relationship with respect to the coefficients. What we have effectively done is taken the one-dimensional x values and projected them into a higher dimension, and then a linear fit can be applied to try and account for the more complicated relationship that may exist between x and y. So this is also related to the idea of applying kernels to features to transform the feature space into a new space where relationships between features and response variables are more easily understood or explained. What does that mean? Why am I just saying this? Well, when you go into machine learning, you're going to hear something called a kernel trick a lot. And there's a lot of these kernel-based methods. And the idea would be that you say, well, it's kind of hard for me to find or learn the relationship between my features and my response. But if I could just transform my feature space into in some way, then maybe like linear methods, linear types of analyses could be applied, and that's often true. So this idea in regression is something it's kind of laying the foundation for a very similar concept that is widely used in the machine learning and data science realm. So I want to just be touching on this here because I'm trying to lay the groundwork for the types of methods and procedures that you'll see in more general machine learning methods. So I'm going to show you how to transform the data by hand to fit a quadratic. What I'm going to ask you to do is add comments to each of the code cells below to explain the individual lines of code cell. You do not need to add comments to the lines I've already provided comments for. So with that, I think actually if you haven't already, I would recommend pausing this video and trying to go through this, add your understanding of what each line of code is, because I'm going to just say what they are. I'm not going to add the code comments. And then I'll just continue to go through this activity. But I think this is a good place for you at this point. Pause it, go through everything, this activity on your own up until this last part right here, and then we'll pause the video. I'll suggest you pause the video again, and then I'll show you how to solve this last part. So just go ahead and take a moment. So first I'm going to import copy as CP. You might remember seeing this in module 4 in the prologue lecture, where I want to create copies so that when I assign variables and they're pointing to like a data frame or an array or something, I can then have this copy that I can change without changing the original thing because of the kind of the pass by reference aspect of how changing data works. So we're just going to import copy as CP. I'm going to create a copy of my X data. Remember, I imported this before. This is the TV sales data. And what I'm going to insert to the right of this, so if I look at X2, like this is a data frame. So let's just look at X2. I'll just go ahead and do this right here. You'll see it has these 200 rows by 1 column. So it's this data frame. That's just like that. Now I'm just going to go ahead and delete that. I'm going to insert in the in column 1, remember Python indexing 0, so that first column is index 0. I'm going to insert to the right of that, so at 1 there, I'm going to have the squared TV data, and I'm just going to take that TV feature and square it. And now when I do that, when I insert it there, and I look at X2, here's that data. It's the TV and the TV squared. That's all I've done. I've just squared all the entries that were over here on the left. And it's just inserting it to the right of TV. So it's in column 1 now instead of column 0 because of Python indexing. So now I'm going to create my second linear model, LM2. So I'm instantiating. Remember the process. I've already imported, so I don't need to import again. I'm going to instantiate, and I'm going to fit. And I'm going to fit with the X2 data frame. So now there's 2 features, the TV and the square of the TV expenditure data for advertising. If I look at the intercepts and the coefficients, you see the intercept is different now. It's 6.11, and I have 2 intercepts, or excuse me, 2 coefficients. One is associated with the linear term, and the other one's associated with the quadratic term. And so now if I look at the R squared value, I see it's about 0.619. Well, let's look at what it was before. It was 0.6118. Okay, so 0.6118 and 0.619. So that's not much of a change. Again, if you look at this data, like here it was here, I wouldn't say that there's a strong evidence to suggest that a quadratic model is really appropriate here. But it is a slightly better R squared value, but it's a more complex model, and I didn't get much better in terms of explaining the variation of the data. So it doesn't seem like a quadratic model is much better. I scrolled too far. But it is slightly better. So what does this look like? Well, I'm going to do the following. I am going to create this new data frame over here, and I'm going to have that same thing where I create this. Now I'm going to create a lin space for the min to max values. So I'm going to do this over kind of a different space. So I'm just actually going to run these, and we'll talk about what was done here in a second. So okay, here's the output. You can see the difference between the quadratic and the linear model is fairly slight. Like there's not much visual justification, even qualitative justification from this picture to suggest that the quadratic was necessary to adequately or accurately explain the variation in the data compared to the linear. But as far as what was done here, I created a new data frame with two features, two columns. There's the TV and the TV squared, and then I just took the min and the max data for the TV, and then I also took the min and the max data for the TV and squared it. Excuse me. I took 20 data points from the min and the max in each case, and here's where I'm squaring that other array. So that's all that's going on here. I'm showing the first 5 rows with that head. When I create my quadratic predictions, all I do is feed in that data frame, and you can definitely see why you needed to have like 2D arrays. It's generally expecting more complicated models, or at least more features than just one, because that's often the case. You have multiple features that are going into your data. Even if it's not TV and TV squared, we do know that we have TV, newspaper, and radio ads expenditures. So we know that there's at least 3 features that we should generally be looking at, even though we're started with a simpler model. So we have our data frame with the multiple features. We feed it into our second linear model, into the predict method of that second linear model. And that gives us our quadratic predictions. And then we created our scatter plot, and then we had our linear predictions from before, and now we've just added what is new when we look at the range of the x new 2 values. I wanted to plot a quadratic. 2 points isn't enough to represent a quadratic, to make kind of a smooth looking parabola. So it was necessary for me, that's why I used 20 points here, was to just, excuse me, get a slightly better looking quadratic. And then I just, plot those quadratic values that were obtained from above. I'm doing that in black just to differentiate it from the line so it's visually easier to see. That's it. That's all that was going on here. So your comments should reflect, simplified versions of the things I'm saying. And then the last thing here that I'm asking you to do is to create cells below this that repeat this above process for a cubic approximation. Then I want you to try something silly like a 6th or a 10th order polynomial approximation. And I want you to think like, what is the best model and why? Which again goes into thinking of the complexity of the model and the R-squared value together. So here I'm going to pause. I suggest you try to do this yourself and then compare to what I'm going to show you when we come back in a second. All right, so now we're going to see my solution, or at least partial solution, for this part of the activity. So I'm going to show you how to repeat the above process for a cubic approximation. Along the way, I'm going to suggest how you maybe want to go about doing the 6th or 10th order, something that I'm suggesting you do, and they're actually asking you to do. You are instructed to try something silly like a really high order approximation, just so you go through the process for yourself to try to code that up. And then you also need to provide this explanation of what you think is the best model and why. And I've certainly provided plenty of my own opinions on the matter in the video so far. So the first thing I'm going to do is just go ahead and start with a copy of the x2 data set, which was the quadratic data set. I'm going to create a copy of that, call it x3. I'm then going to insert into the second column 2, which would be column 3 because of Python indexing, the cube of the TV expenditure data for advertising dollars. And I'm just going to look at it just to make sure it works. You see the x3 table. I have TV, TV squared, and TV cubed. If I'm going to make a cubic approximation, I need to have the TV, TV squared, and TV cubed. It's not an option. If you skip over this, it's wrong. If you just have TV and TV cubed, that's not a general cubic approximation because you're not having the squared term in there as well. If you're going to go to a 6th order or 10th order, you're going to have TV, TV squared, TV cubed, TV to the 4th, TV to the 5th, and so on. And you could manually go through and code up all the lines to make sure you insert all of these columns. That's up to you. You don't necessarily have to manually do it. You could do a user-defined function. It's just something I'll get to below about managing the data set to make sure you have all the right columns in there. So then I just make my third linear model. I instantiate. Remember, import has already been done. So now I instantiate and I fit with the x3 data and the y. If you have code comments here because you're copying and pasting like I did, but I didn't have code comments above, you should update your code comments if they were specific to the quadratic data we were looking at above. I'm then just looking at the intercept and the coefficients. So there's of course these 3 coefficients now. So here's this intercept, and there's just the coefficients are different again if you compare them to what we've had before. The R-squared value has gone up again very slightly for the level of complexity we have. And then I went ahead and created a user-defined function here just to create a data frame that has the min to max TV features. And you're going to pass it the data frame that you want. the order of the data that you're working with in terms of the polynomial order you want. So in this case, I'm going to pass like a 3, as you can see below. And then a default number of values that are useful for plotting to go from the min to the max. So this is just kind of replicating what I was doing above here, because as things get more complicated, I just don't want to write this out with more and more rows in this dictionary, because it's likely to have a typo. Because I'm going to do a lot of, if I would do a lot of copy and paste that way, I would go to the cube, the fourth, the fifth, especially when I go to the higher order model, and it's very easy to misalign, screw something up with the copy and paste. So anything that is kind of redundant and requires maybe copy and paste and editing, it's a good idea to think of a function to do that. So in my function, I create my min to max data set. So here's my linspace, my min to my max of that TV data. That's the TV expenditures, the min and the max values obtained by these min and max methods associated with that series, that feature column from the data frame that is passed to it, and then the number of data points in, which I could always change, but I just defaulted it to 20. I then, I could pass to something else. I'm using the default value below. I then create my new data frame initially with just the TV data with the min to max data. That's my first column. And then I start looping through the orders here. So I go from 1 to order. Now there's Python indexing going on here. So when I'm at that first, the column 1, that's really column 2. So that's the TV, data that should be raised to the second power. So that's why I'm taking I+1, casting as a string, concatenating that to TV to that power, because that becomes the column name, what I'm calling the feature name. You can also call it the column name. I'm then inserting into the ith column, indexed by I, named with that feature name, that min to max data, and then it's again raised to the I+1 power. That's it. It's a fairly simple function, but this ensures, like, if you were to do this when the order is 6, this will create the min to max data. Now, this is just for the purposes of plotting. If you actually wanted to use this, let's say, to do this process here, what I might do is, create like x3 as a copy of the original x data, and I would perhaps have another function that would do the process like I was seeing here, where I would, instead of having this linspace, I would just have maybe like, new TV data frame instead of min max, and which is really useful for plotting. I could create a new user-defined function that was just, let's say, new TV data frame, and maybe I just pass data and order to it. The in is not a good idea there, and I would then just I would instantiate my data with the TV data, and I would just have data.tv right here, and then I would do something very similar to this, except this would be that, that data.tv raised to the I+1 power instead of the min-max data. So this is just if I want that min-max range, and it's useful for plotting and predictions. But if I wanted to encode this process so that I could say, okay, I want to look at it if it was a 6th order linear model, or a 10th order linear model, or a 20th order linear model. I don't want to write it in like over and over, insert, and continue to hope that I don't make mistakes in terms of changing that power. I should really encode that process where I'm copying X and then creating that X data, and then I just keep inserting new feature columns in a loop effectively to do it. So that's something I'd recommend. I'm not doing that here because I want you to kind of maybe work a little bit with that. If you have questions, again, you can post a discussion board, I'll help out. But just moving forward, I create my new data set, my new data frame for my 3rd order. You can just see it's doing what I want, where these are there's 20 rows here, so it's 0 to 19, and I have my TV data, my TV squared, and my TV cubed, and it's going from the min to the max. This is just ordered data sets useful for predictions and plotting purposes. So then I make my cubic predictions on my 3rd linear model that I've fitted here, and then I just added things to my plots. You could also add labels and a legend. That's not a bad idea. And then I can just see, okay, in green is my cubic, and red is my quadratic, and my line is still, or no, my line is in red, my quadratic's in black, my cubic's in green. My apologies if you're colorblind, it's a little hard to see. But you can kind of tell, like, there's not a lot of benefit in going to these higher order models here. The linear model seems to generally be doing the best, at least for the level of complexity. But see what happens when you go to 6 or 10. You'll probably start to see that you capture this kind of tail a little bit better, but it's kind of overfitting. You're just kind of making sure the curve passes through there, but then you kind of pay the price in other places. So anyways, you need to do that. You still need to Go try something silly like a 6th or a 10th order, 20th order, especially if you functionalize some of the processes I was talking about in terms of creating a data frame. It's very easy to create something of an arbitrarily like high order. And then just what do you think is the best model and why? You might disagree with me. So with that, you should probably pause the video, try finishing that activity or comparing what you had to what I was just saying, or trying some of these functional approaches to manipulating the data. And then when you're ready, continue on as we talk about multiple linear regression. So for multiple linear regression, it's pretty straightforward. Simple linear regression is easily extended to include multiple features. And it's just called multiple linear regression. So we just basically say like I have beta naught plus beta 1 x and so on to like beta sub n times x sub n, where I have maybe n features. I just have these n coefficients. It's kind of not much different than what we were seeing with the polynomial regression, quite frankly. It's very similar, in fact. So each x represents a different feature, and each feature has its own coefficient. In this case, you have beta naught plus beta 1 times TV plus beta 2 times radio plus beta 3 times newspaper for the case study that we're looking at in this lecture notebook. So we can estimate these below. So now if I create my feature columns, and it's this list of these names associated with the column names of my data frame, and then I create now, I'll call it a matrix X, kind of in that sense. X has that data that's from those feature columns. Y has the data that's again from the cells. I instantiate, this is my multiple linear regression model, LM underscore multiple. Again, you can rename these whatever you want. I just try to have like LM for linear model, and then just, kind of subscripts, if you will, with that underscore that are descriptive in some sense, or just helpful to distinguish the different linear models. But I instantiate and then I fit. Notice it's the capital X here because I use capital X here to have the multi-dimensional feature space here, which again isn't much different. I mean, at a computational level, it's like not different from the polynomial regression we were just looking at in activity 1. So after I do that fit, then I can look at the intercept and the coefficients. Excuse me. You can see the intercept, you can see the different coefficients. Quite a bit different than what we had before, because now we have the coefficients for the TV, the radio, and the newspaper. And then, of course, there's the interpretability of these coefficients. If we increase $1,000 in TV ad spending, then we get, it looks like 45.765 widgets, because those are in units of 1,000. And then you can see that you get more, it seems like, sales in terms of $1,000 added for radio. And is that right, radio? And then I think this was newspaper. You see it looks even kind of small, and it's very close to 0, and then it's negative, in fact. So you could, how would you interpret the other coefficients? This is a good place. It's not an activity, but maybe you should edit this for yourself to see if you can write down clearly how you interpret these things. That's a good idea. And when you're done with that, maybe pause, do that for yourself, and then continue watching about feature selection. So feature selection, what does that mean? Well, it's really a question of how should we decide which features to include in a linear model to balance simplicity with the goodness of fit. Remember how I was talking about the polynomial regression? You can increase the complexity of the model by using higher order polynomials. You could also, if you have lots of other data you're collecting that you think are features, you could throw them all into your data set and use them all. It doesn't mean you should. So how do you figure out, like, what's the simplest model that does the best job? Well, you kind of have to try different models and keep just the features in the model that result in larger coefficients, because those seem to explain, most, right? When a coefficient's relatively small, kind of doesn't seem to explain anything. Like, that's near 0 when you think of the units involved here, especially. You kind of go, like, is that even a meaningful value or feature to include? And it certainly might tell you that you shouldn't spend your money. If that's something you're spending your money on, it doesn't seem to have an impact on sales at all in, relative terms compared to these other values. So, it's sometimes useful to just consider the most complex model and then start with kind of trying to simplify from there. You can check whether R squared value kind of keeps going up when you add new features, except it generally does. What are the drawbacks to this approach? Linear models rely upon a lot of assumptions, such as the features being independent, right? I haven't really talked about any of the assumptions about why this should work, or just kind of the mechanics of making this work in code and a little bit of the concept. So if the assumptions are violated, which by the way they usually are, then R squared and other statistical values used to assess goodness of fit or the importance of a coefficient are certainly less reliable. you should take a class on regression. We have a class at CU Denver on applied regression. Highly recommend you take it. We have some OER materials that are being developed by Dr. Joshua French. They are on the GitHub institution that is associated with where the repo that holds these materials are. He's producing this book. I highly recommend you learn more about regression. So I'm just kind of showing it as a case study of where we learn models from data, but there's a whole class on regression that I highly recommend people take. And again, R-squared is susceptible to overfitting, and there's no guarantee that a model with a high R-squared value will generalize, meaning it doesn't necessarily do a good job of predicting data you haven't seen already. So again, I want to just emphasize R-squared will always increase as you do add more features to the model, even if they are unrelated to the response. Even if they are unrelated to the response. Thus, selecting the model with the highest R-squared value is not a reliable approach for choosing the best linear model. There is an alternative to R-squared called adjusted R-squared that penalizes model complexity to control for overfitting, but it generally under-penalizes complexity. So again, if we look at the score here, this R-squared score, we see it's like 0.897. That is significantly higher than what we've seen for the linear regression so far, which is the TV dollars, advertising dollars spent, where we're really seeing like low 0.6. So that seems good, but you might look at this and say, what would it be if I just got rid of the newspaper? What if I just had TV and radio? Again, pause the video, try that for yourself. What if you come back here and you change your feature so that you remove newspaper, you just have TV and radio? What if it was just radio instead of TV? How would that work? You could redo some of the analysis we've already done in this notebook with radio instead of TV or newspaper instead of TV. There's a lot of things that you could play with here just to try to do your own experiments and see if it matches maybe a little bit of the intuition that hopefully you're developing as you go through this. But in the end, we're going to come to this kind of question. Is there a better approach to feature selection? The answer is yes, cross-validation. It provides a more reliable estimate of out-of-sample error. It is therefore a better way to choose which of your models will best generalize to out-of-sample data. There is extensive functionality for cross-validation in the scikit-learn library. These are beyond the scope of this class for sure. I highly recommend, again, that you just continue with your journey. Like take more advanced statistics classes, take more advanced math classes, take more advanced machine learning and data science classes. But you have to really take some more foundational math and statistics courses in order to really understand what's going on in the math behind a lot of the machine learning algorithms. We're just kind of dipping our toes into this and seeing kind of the workflows and how we can use some packages to do some of this work for us. But if you really want to understand how this works and what these methods mean, you should really take a more advanced class. And we'll talk more about this, cross-validation idea in a future extra lecture. I'm still developing some of these materials, so it might not be up on the repo for a little while yet. But with that, I recommend that you kind of just pause the video again, look at activity 2, see if you can read through and do it yourself. And then you can revisit the next part of this video that will keep going, where I'll first go through the instructions, and then I'll look at providing some of the answers to things as we go through it. So in activity 2, we will see how to handle categorical predictors with categories. You should read through this section very carefully. Look for the highlighted questions, problems that you need to answer. So up to now, all of our predictors have been numeric, right? We looked at dollars associated with TV, radio, and newspaper sales. So those have been the predictor variables, also called the features. Features and predictor variables are the same thing. Response variable is the feature kind of the data that is the function of the others. So what if one of our predictors was actually categorical in nature? So it was more like a label, not a number. So let's create a new feature called size and randomly assign observations to be small or large, defining the size of the market. So you might imagine that you could say, oh, I have maybe really large markets defined by a certain amount of population that's in the market where I'm spending advertising dollars. And I can just say there's certain large markets I advertise in and certain small markets I advertise in. Just for the sake of argument, we randomly distribute these because this is just a fake data set we're playing with. But you could certainly imagine that you maybe even have like, and we'll get to this later in this activity, like we'll have urban, rural, suburban type areas. Maybe that there's different categories of like Eastern US, Midwest, Western US, where you're spending your advertising dollars. And those are just labels associated with certain markets. And you'll want to maybe take those into account with your models. So we're going to see how do we do that. So first, We're going to import numpy and p if you don't already have this done. This was done elsewhere in the notebook. But I'm just going to set a seed for reproducibility. So I'm going to set the seed to just 1, 2, 3, 4, 5. This is just so that if you run this once and everything else through one time, wherever there's that randomness generated, it's the same for me and the same for you. So I'm going to create a bunch of random numbers. That's the length of my data. And then so that's the 200 in this case because of the size of the market. I'm going to create a mask for what a large market is. And that's just going to be, I'm just going to say maybe roughly half the markets should be large. So this is a rand number, not rand in. So rand in would be random normally distributed. Rand is uniform random numbers between 0 and 1 if you don't change anything. You might remember that all the way back from module 2 when we were playing with random number generation. So if my random numbers happen to be greater than 0.5 anywhere, I'm going to then say that I create a mask that should be 0. Or excuse me, 1 should be 1. That's what the value should be if this is happening. It's like a true, basically. And then it should be false or like a 0 elsewhere. And so then I'm going to just say I want to initially set the size of all my markets to small. And then I'm going to see that if that mask large has been set, so if mask was greater than 0.5, then I want to change those to large. So it's just a very simple way of doing that. Kind of initialize everything to small and then use this mask as changing the ones that I've randomly deemed to be large to large. So that's what's going on here. And if you look at it, you'll see, okay, it looks like that first number. And in fact, we can kind of play around with this a little bit. This is a great place for me to put in fact, a scratch code cell and just look at some of these nums. Right, and you can see with these random numbers that are generated, like I have this number, which is, you look at with that scientific notation, the first number is like 0.929, so that's certainly greater than 0.5, so that was a large market. The second number was about 0.3, maybe I'll actually do it more like this. Let's just look at like the first 5 of these. So we have 0.929, that's greater than 0.5, 0.313, that's not, 0.183 is not, 0.204 is not. So we have like large, small, 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 and then this is 0.56, that's greater than 0.5, so that was large. If you wanted to see what the masks look like for mask large, just here I'll just do again like the first 5. So it's true, false, false, true. So it just this operation just creates an array of trues and falses where they're trues wherever this condition was true. This is just kind of a shorthand for doing that. And then I can pass an array of trues and falses here, and wherever it was true, it then just set the value to be large. So just a little bit of a kind of a shortcut coding technique for doing that. And again, I'm using that .loc here because I'm associating this with these feature calls instead of iloc, which was just all indice-based location. I actually want to set it with the size feature that I've added to the data. So what is the map method in the code cell below doing? This is a question for you to answer. So for scikit-learn, we need to represent all data numerically. If the feature only has 2 categories, we can simply create a dummy variable that represents the categories as a binary value. So just because we have categorical variables doesn't mean that scikit-learn knows what to do with them. We actually have to assign them a number. Not that the number has to mean anything, that's why it's a dummy variable, but we just have to have numerical values to work with. So what we're going to do is we're going to look at data is large, and what we're going to do is use this map. Right? And it's basically just defining a function. That's what it's doing at the end of the day. So this is something you should answer. You should fill out this, answer this like below the question. This is what it's doing. So basically wherever the value was small, it's getting assigned to 0. That's what this dictionary is doing. It's mapping small values to the value 0 and large values to the value 1. So now if I do that for the data on this, for like this new feature, that I'm creating a new feature, is it large or not? And so you see it's just being, every time you create a new feature, then what happens, it just gets inserted to the right on the data set. So we have our TV, radio, newspaper sales. We had size, that's what we did above, right? As soon as we did this, it just populated all the smalls with a value small. This changed some of them to large. So this is then mapping all the large values to 1 and the small values to 0. And that's exactly what we see here. Large is 1, small is 0. So now we can redo multiple linear regression and we can include is large as a predictor. We couldn't include size because it just had categorical variables in there, large and small. But if we have is large, that has zeros and ones. So now if we have that as a feature and we recreate that X and Y data sets and we do our linear model, I'm just overriding things now. So I instantiate and I fit. It's that same process over and over again. And now I'm just going to print, just because there's enough, like there's 4 different features here, I'm just going to use a little zip. I'm going to do something, just using some things we've seen before just to revisit certain coding concepts. And I'm going to just print what the feature name is, that column, the feature columns, because that's just coming from this list, and a corresponding coefficient from the linear model. So then when I print that out, I see, okay, TV 0.0457, radio 0.1887, newspaper negative 0.001. We've seen these values before. And is large 0.057. Now, is large as opposed to is small is because we have 1 if it's large and 0 if it's small. That's a good way to think about that. So what we're saying is like, oh, if it's large, right, how do we interpret this? It's 0.057. So how do we interpret that coefficient? For a given amount of TV, radio, newspaper ad spending, being a large market is associated with an average increase in sales of 57.42 widgets as compared to a small market, which is called the baseline level. Okay, so if we had reversed the 0-1 coding and created the feature is small instead, the coefficient would be the same, except it would be negative instead of positive. Again, good thing for you to try, play around with, but maybe remove it from the activity or try it in create a copy of this notebook and play around with it somewhere there, because it will just kind of maybe muddy things up a little bit if you leave it all in here. Or you could create scratch code cells and play around a little with it, or create a copy of your data frame and do it on that one. Play around with it, see what you want. But that's something that you could do. I highly recommend it. So but just the point of that is your choice of category for the baseline does not matter. All that changes is the interpretation of the coefficient, and it's going to be equivalent. It's just my baseline is now a large market, and then you'd see, oh, if I go to a smaller market, I would see a decrease in sales relative to the baseline, because now the baseline is a large market. That's all that would happen. So again, doesn't matter what you choose for the baseline. Just something that's useful to keep in mind is maybe choose a baseline where the interpretation makes the most sense for you and you don't mess it up. So then we'll get to this part of handling categorical predictors with more than 2 categories. But I just say I'm going to pause the video now, or you should pause perhaps, play around with some of the things I was saying, like this is small, and then come back and we'll continue to go through this activity. We now see how to handle categorical predictors with more than 2 categories. So below, what you're asked to do is to print out and comment on what the mask suburban and mask urban variables are and how they are being used. I'll be showing that in a scratch code cell, but you should really be doing it within the notebook. That's what I'm asking you to do. So create your own code cell and print it out. So we're going to create a new feature called area. And we're randomly going to assign observations of that to be rural, suburban, or urban. So this is kind of like how we had markets that were large or small. This is just a different categorical variable, but instead of 2 categories, like large and small, we have 3, rural, suburban, and urban. So as before, we create a random seed just for reproducibility, and here we're going to set it to be 1, 2, 3, 4, 5, 6. We create our random numbers as we did before, but now we have 2 different masks. Instead of 1 mask for like the large, whether something was a large or small market, we now have mask for suburban or urban. So you can see that we're first creating rural as our default, as our baseline, and then we're using these masks to set an area to either be suburban or urban depending on the particular conditions. So here I'm saying there's 3, and I'm kind of dividing up the interval 0, 1. So again, I'm producing these random numbers between 0 and 1 because I'm using rand instead of rand-n, and I'm just having it as default rand, which means the location and scale parameters are 0 and 1. So it's just between 0 and 1 is what's going on within that. You can again read the documentation and also review what we did back in the module 2 when we were playing with some random number generation. So if my random numbers that I've generated are greater than 0.33 and less than 0.66, so that's roughly a third, like the middle third of the interval between 0 and 1, then mass suburban will be true. Otherwise, it'll be false. And then mask urban is going to be true if it's just greater than 0.66. So basically, if these numbers are strictly, or not strictly, less than or equal to 0.33, then the region will stay the baseline, the rural. So this is just, I'm just randomly distributing this. In general, these are features that would be, or data that would be collected along with your data set. You wouldn't just be randomly assigning things, but it's again just for illustrative purposes. So I'll go ahead and run this here. I've already said how these are being used. If you wanted to see what they are, you should create a code cell and show this to print it. But I'm going to go ahead and create a scratch code cell. And I'm just going to go ahead and show you what like mask suburban looks like. And oh, it would help if I actually type things in correctly. And also I said you should do a print command. So mask suburban. There we go. And it did not like that. So why? Oh, mark, because I can't type. That would be why. Okay, they're mass suburban. So you see there's a bunch of falses and then some trues. And where is that first true that I see here? It's it looks like it's the fifth one, and then there, of course, we see there's the suburban right there. And we see rural, urban. So, okay, if we look at the mask for the, let's say, the urban area, it looks, if I can type it correctly again, if I print that out, we see false, true, false. And of course, yeah, we see urban as true in just the second and fourth positions, which is consistent with what we're seeing here. So there you go. It's very similar to what we did before when there's two categories. You just have to create different masks. So if there's two categories, you need one mask. You define like your default region, and then you have your mask applied for the other condition. If there's 7 different categories within your categorical variable, so I don't know why that would be. I mean, well, let's say there's age ranges. Sometimes they'll say, are you, is it less, are you 18 years or younger? Are you, 19 to 29 years old, 30 to 40, and so on. So you can imagine there could be like maybe 7 categories for age. And in that case, if there's 7 categories, you would have like maybe your baseline, which is maybe under 18. And then you would assign the age ranges using 6 different masks for the other 6 types that haven't been assigned. If you were to do something like that, if you're creating kind of a synthetic data set like we're doing here just for illustrative purposes. You could also have another data, like this data could be collected elsewhere and you could just read it in. Like it could just be the values are just there and you just need to have the mask set. So you might read it in as a column data and then use the mask, this way of masking based on that data set in order to assign it to the other data if it happens to be numerical or something in that sense. Anyways, we have to, again, represent the area numerically, and we can't simply code 0 for rural, 1 for suburban, and 2 for urban, because that would imply an ordered relationship between suburban and urban. Somehow urban is like twice the suburban category. So what we need is another dummy variable. So you just want to do 0, 1 encoding. And so this means that when I look at like my area dummies, if I look at this, I'm going to create another dummy variable. So I'm going to create 3 dummy variables effectively. You're going to see how this works here in a second. So here we go. I have area suburban, area urban. And if area suburban is 1, then it's suburban. If it's 0, it's not it's suburban, but it could be urban or rural. So then I need another variable because to distinguish whether it's urban or rural. So basically the way you interpret this is a 0 and a 0 here means it's rural. And you see that's exactly what's going on. 0 and 0 here is rural in this first column. So 0 and 0 go with rural. And a 0 and a 1, of course, is an urban because it's 0 for the suburban and it's 1 for the urban category. And 1, 0 would be suburban. So it's pretty self-explanatory kind of once you see it, but I don't want 0, 1, and 2. So I just described this here again in words to interpret that coding. Again, I need the 2 dummy variables, not 3. 2 dummy variables captures all the information about the area feature, and it implicitly defines rural again as the baseline. So in general, if you have a categorical feature with k levels, so like when I was talking about like if you had 7 levels, I would need 6 dummy variables. You need k minus 1. So if there's k levels, you need k minus 1 dummy variables. That way you can do this 0, 1 encoding, so that like all of them would be 0 except 1 if it was one of these categories, or they're all 0 and then it's the baseline category. You just need to do that so that you can make the linear regression work and interpret the that coefficient with respect to these categories that are 0, 1 encoded. So again, if I add the area suburban and area urban to my feature columns and I update my data set X and Y and I instantiate and fit, again, I've already imported, so I just do the instantiate and fit, which is where the learning of the parameters comes in, and I run this. I see here's all these different coefficients, and we see here's this area suburban is negative 0.1, here's this area suburban is positive 0.268. So again, the sale, this is with respect to like the amount of sales that are increased here, and the sales were in units of thousands. So how do we interpret these coefficients? If we hold all other variables fixed, being in a suburban area is actually associated with an average decrease in sales of 106.56 widgets as compared to the baseline level, which is rural. So what is this telling you, right? If you're doing the same type of marketing, let's say, it's the same types of ads that run in all the markets, these ads are not effective in the suburban area, or at least your product is less popular in the suburban area. That's probably a better way to think of it, because this is holding everything else fixed, whether you're advertising or not. But your product is not selling as well in a suburban area compared to the rural or urban. That's the proper kind of interpretation there. Or certainly with respect to rural, I'm sorry, the rural is just the baseline. So going to suburban from rural, you're going to lose some sales. So your product's very popular in rural areas, at least relative to suburban. But we actually see being in an urban area is associated with an increase of sales of 268.13 as compared to rural. So if you looked at that, you might start thinking about markets. If you wanted to target a new market, where's a new market just to generate some more sales, you would probably think urban or rural, depending on maybe cost factors and getting your product there. And you would maybe shy away from trying to target more suburban areas as trying to ship your widgets to, because they just don't seem to be selling there compared to the other areas. So that's a good way of interpreting this and maybe coming to some sort of decision, a policy, a recommendation for a client if you're using regression and you're trying to think of how to interpret and use this information or interpret this in a useful way for somebody. So one final note about dummy encoding, and then the final part that you have to do for this activity. If you have categories that can be ranked, like strongly disagree, neutral agree, strongly agree, you can potentially use a single dummy variable and represent the categories numerically, such as 1 through 5. So if they're ranking like it's, somebody's doing like a perceived quality, or, they're giving like a 5-star review out of 5 stars or something, it would make sense to say like, well, 5 stars is a ranking of 5, of course. But, even like these kind of, qualitative assessments can be, quantitative in their, or it makes more sense to perhaps represent them quantitatively instead of categorically in a ranked ordered way, like 1, 2, 3, 4, 5. So that's just something to think about. Like what I'm showing is more like there's no reason to maybe say suburban should be 2 or 1 or 0. But the 0, 1 encoding is more of a way of just assigning like false and true with the zeros and the ones, so that you have a good interpretation of what these values mean relative to a baseline case. And you can choose the baseline. If you chose suburban as the baseline, then this sign of this one, for instance, would switch, and the value of this would potentially change because it would be compared to the baseline of the suburban. Again, it's a good place to pause the video and see that for yourself. Maybe make the mask for rural and urban and get rid of the suburban mask. And so then, play around, see for yourself how things change and what the interpretations are. And then finally, before the end of activity 2, what you need to do in the code and the markdown cells below, and you should definitely add more than what I have here. I just have one code and one markdown cell. Repeat the same above analysis that I was just doing with these, with this category, this categorical variable with 3 categories, where you have 4 new categories, where you add 4 new categories to the data. Now, I would call these 4 categories. What you should do is ET, CT, MT, and PT to indicate the Eastern time zone, Central time zone, Mountain time zone, and Pacific time zone, the typical 4 time zones most people reside in within the contiguous United States. You get to choose how to randomly assign these categories to the data. I recommend do a little Google search, like what's the percentage of the population in the US? And then you could kind of maybe distribute the markets randomly based on kind of intervals that are the size, a proportion of the size from 0 to 1, non-overlapping for each of these regions, that are proportional to the amount of people living in each of these time zones. So you try that, code it up, and you're just basically doing what I did. I just want you to go through the process, and so I'm not going to show the solution here. You really should think about what is it you need to change. You just need to copy and paste what I'm doing, change some variable names, and just be careful. You're going to have 4 categories, so you need 3 masks. And you should make sure the names make sense and make sure that these regions kind of make sense as well. And I would do it based on population distribution. And then, just make sure to explain interpretations of what all the values mean. So you can kind of just copy and paste like the code and mark down cells related to this part about handling categorical predictors with more than 2 categories. So like kind of all the way up to here. And then just change it so that or add to it, I should say, where you have these time zone categories and you distribute everything and interpret stuff. It's a good thing for you to do. It's going to help drive home some of this interpretation and understanding of the model, that you learn from this data that you're creating. Doing that will then end activity 2, and go ahead and maybe try to do some of that now, and then you can come back and I'll just close this video with a little bit of a discussion of what we did not cover. What have we not covered in this lecture notebook? Well, we haven't covered actually a lot. We haven't covered how to detect collinearity. We haven't covered how to diagnose model fit. These are all things you could Google, like these various topics. We haven't covered how to transform predictors to fit nonlinear relationships. And that's what I mean is more like more complicated nonlinear relationships than just like monomials. We've seen that one for higher order polynomials. We certainly haven't covered nonlinear regression. We haven't covered interaction terms, the assumptions of linear regression. Haven't really talked about those much, and a whole bunch more. You could certainly go very deep into linear regression and learn how to apply it really, really well. And that's an excellent way to start your modeling process when working a regression process. However, it is limited by the fact that it can only make good predictions if there is a linear relationship between the features and the response. And this is why more complex methods with maybe higher variance and lower bias will outperform linear regression. So what you want to understand, while you want to understand linear regression conceptually and understand its strengths and weaknesses and be familiar with the terminology and how to apply it, we also want to spend time on many other machine learning methods, which is why we aren't going deeper here. Where you could perhaps go into much more depth, as I mentioned, I think earlier in this video, as you can see, Dr. Joshua French's OER textbook, A Progressive Introduction to Linear Models. So if you click on this, this actually goes to our GitHub organization setup for our OER project, and it's a nice open textbook, and he shows a lot of things. It's using the R language, so that's a great place to start. It's fairly advanced class. It's a 4/5000 level class, and it's taught regularly here at CU Denver. There's also some videos. I linked to kind of some things here, or a quick reference guide that you could also look at. And again, don't forget to do your summary activity. So that's it for this video, and I will be working on and getting some additional materials, supplemental materials, optional materials for people to look at that involve artificial neurons and classifiers, posted to the GitHub later. It depends on when you're watching this video, if these materials are already available, and if they're either optional or something that's assigned in the course regularly. It kind of depends on the pace in a given semester, whether we get further than this. But hope you enjoyed this, if this is the end of the class for you, and if not, I will see you in some future lecture notebooks.